So today we're going to be looking at the binomial distribution. First, let's recall what we did the other day in this problem. This says that selected boxes of breakfast cereal contain a prize. Let's say that 5% of the boxes of your favorite cereal contain a prize, but the other 95% don't, and they contain the message, sorry, try again. So you get excited, you go to the grocery store and buy 25 boxes of your favorite breakfast cereal, perhaps getting ready for the apocalypse, I don't know. So you're going to find the probability that exactly 2 boxes contain a prize. When you see exactly, we said that that's going to be the binomial PDF distribution that you use because we want exactly 2. So what that means is that in our calculators, and we should write this as our quote-unquote work, is that we're going to use the binomial PDF. Remember, the first number you enter is the number of trials you have, which in this case is 25, since we're buying 25 boxes. The next is the probability of a success. And so because only 5% of the boxes are going to be successful, we put 0.05. And then the last number contains the exact number that we want, which is going to be 2. So again, we put that in our calculator in that specific way. So we use the binomial PDF 25, 0.05, 2. Or if you have the new operating system, just enter the values in, and then when it says paste on the bottom, just hit paste and then enter again, and it'll do that whole thing for you. Anyway, so we go to the nearest 3 decimal places. And so we look at that 0, that 5 tells us to round the 0 up to a 1. So this gives us the probability of 0.231, or a lot of you guys like percents instead, or 23.1%. Then this says find the probability that 5 boxes or less contain a prize. Well, 5 boxes or less means that we can have 5 or 4 or 3, etc., all the way down to 0. Remember, that's the CDF function that we're going to use, the binomial CDF, which is cumulative, which is up to that specific number. And because we do want to go all the way up to 5, that means that we are going to use 5 in our distribution. So we'll use the binomial CDF this time. And this time we still have trials, 25 trials, a probability of 5%, but this time we want it to cumulatively go all the way up to 5. And so if we enter that in our calculator, sorry, it's a little dark. Again, we have 25 trials, 5% success rate, and this time we want to go cumulatively up to and including 5. So to 3 decimal places, that 7 bumps that 8 up to 9. So that means that our probability would be about 0.999 or 99.9%. Then it says how many prizes do you expect to find? And we know that when we have expected value, that's where we take n times p, where n is our number of trials. In this case, that's going to be 25. And p is our probability of a success, which is 5%. Well, we multiply it out and we get 1.25. And I really want to round that to 1 box. But I guess an expected value, just like when they say things like the average American family has, like 2.8 people, we're just going to leave it like this. So our expected value is going to be 1.25 prizes that we would expect to contain. Maybe I should put a unit, I don't know. Okay? So we'd expect in the 25 boxes to get 1.25 prizes, which is just kind of like an average. Okay? So here's the new thing we're going to look at today. We did talk about this, that the binomial CDF function can only add up the probabilities of an event at a specific value and lower. Remember, it goes up to and including that. So for these next questions, we're going to use the concept of complementary events and subtract what we don't want from 1. Okay? So anytime that it's something like more than k, where it's going to be on the other side, that's where we're going to use 1 minus the binomial CDF. So this says find the probability, same scenario, that 5 or more boxes contain a prize. Okay? So that means that we want 5 or more prizes. However, when you think about the lot of everything, that's not what the calculator can calculate for us. The calculator can take off a certain amount. So when you think about all the prizes, and we kind of looked at this the other day when I tried to prep you for it, this is what our calculator can give us, and this is what we want. And so what we need to do is we need to take 1 minus everything else in order to get 5 or more, which means that we're going to take 1 minus the binomial cumulative distribution frequency of 25 trials at a success rate of 0.05. But even though it says 5 in the problem, notice that because we want 5 or more, we have to subtract off 4 or less. When you mess up that number, you mess up the whole thing. You're not really getting much credit for that, okay? So we're going to put that in our calculator. You can just enter that right in. Whoops. So you could put in 1 minus, and then you can take binomial CDF, again 25, comma, 0.05, whoops, comma, and then 4, again, because we're subtracting off 4 from the left, so we can find everything 5 and greater. And notice that we look at our third decimal place, that 1 tells us to keep that value, and so this gives us the probability of 0.007, and you guys, that's really the same as 0.7%. Now it says find the probability that more than 3 boxes contain a prize. Well, here if we want more than 3 boxes, doesn't that mean that we want 4 or 5, etc.? More than 3 doesn't include 3. So again, because we want this, let's think of what we have to subtract off. This is what our calculator can tell us. So what we want to do here is we want to take 1 minus all of this. So we're going to take 1 minus the binomial cumulative distribution frequency using 25 trials, a success rate of 0.05, and 3. So putting that in the calculator, just to save some time, we look at the third decimal place. That 0 says to keep it. So we have 0.034 or 3.4%. So notice that the number in the problem sometimes is the same. This said more than 3, and we use the number 3. But this said 5 or more, and we use the number 4. You really have to think, here's me using my hands, you really have to think about what is going on. So if kind of writing this out to the side helps you, please do that. I'd rather you be accurate and spend a little extra time. So here's a different question. So you're taking a multiple choice test containing 50 questions with 5 choices for each question. Let's say you haven't studied, so you have to guess for every question. It wants the probability of getting exactly 15 questions correct. So we know that in our PDF, for example, because this is going to be exactly, so exactly means we're going to use the regular probability distribution frequency. We would say, okay, so here's our binomial PDF. We have 50 questions, but it doesn't tell us the probability, or does it? Well, if there are 5 choices, how many of those 5 choices are correct? Just 1. So to find the probability, what we would do is we would take, all right, there's 1 correct answer out of 5 choices, and so that really gives us a probability of 0.2. So that's the probability that we'll use in here. If you wanted to put 1/5, then you could, but y'all seem to like decimals anyway. So we want to have 50 trials, a likelihood of getting it correct of 20% or 0.2, and we want to know when there are exactly 15 questions. So we would put that in our calculator, the regular binomial probability distribution frequency, 50 trials, a probability of 20% or 0.2, and exactly 15 questions. Notice that the third decimal place is a 9, and to the right of it is a 9, and that means that we would round this up. So this rounds up to 0.030. And I know it doesn't seem like a big deal to you guys, but putting that 0 in that third decimal place means that that's how specific you are. And again, that would be equivalent to about, that would be equivalent to about 3.0%. And again, you'd want that, that 0.0%, because again, that's how specific it is. So then it says, find the probability of getting a 50% or lower on the test. Well, first let's think about what 50% or lower would mean. 50% of 50 would be 25. So we basically want 25 or less. And if we thought about that, that means that we would want 25 or 24 or 23, etc., all the way down to 0. And isn't that what the calculator tells us if we use the cumulative distribution frequency? So because, again, the calculator tells us everything to the left, just like that chart with the normal distribution, everything always tells us stuff to the left, then we can just use the regular binomial cumulative distribution frequency. We don't need to subtract it from 1 because the calculator does tell us everything that value or below. So we have 50 trials, that probability of 20%, and then this time we want to see the cumulative all the way up to 25. Okay? So what happens is that if we put that in our calculator, notice we get 0.9999. And so notice that that 9 tells us to round that up to 1, okay? And so what you would say is that what we do is that we can say that that is about 1.000 or about 100%. Or if you wanted to cover your butt a little bit, you could say, you know, just under 100%. But I mean, if you just want to just be safe and use rounding rules, I know it freaks me out too, but that's what you'd want to say. Oh my gosh, and I would need to put this 0.0. I'm a bad teacher. Okay. All right. But that's what you would want to put there. That if it does end up like that, then it is about 1. I mean, that's so close to 1. The moral of the story is if you guess, you're going to get under 50. Okay, so find the probability of getting at least 10 questions correct. So at least 10 questions correct means that we could have 10 or 11, etc. However, remember, the calculator only tells us what's below it. So this is what we want, which means that we would have to subtract off all of these guys, since this is what's in the calculator. So since this is what we want, we would have to take 1 minus all of this. So we would take 1 minus the binomial cumulative distribution frequency using 50.2. And even though the question says 10, notice that we're subtracting off 9 or less. And if we put that in the calculator, again, you can just put it in as 1 minus, like just put the whole thing in. We had 50.29. This time we have 0.556, and notice that that 2 tells us to keep the 6, so we have about 0.556. or 55.6%. Oops, sorry. All right, so we get about 0.556 or 55.6%. So how many questions do you expect to get correct? So remember that that expected value is n times p. So our n is 50. Our probability we found was 0.2. And so we end up getting an expected value of 10 correct questions. Okay? So that's kind of the gist. Let's flip to the back. And I know this says your turn, but since I'm given video notes, we'll kind of talk through this together. So this says during the playoffs, Crosby made 19% of the shots on goal, which was 15 out of 79. And that was much higher than the regular season rate of 13.9%. So does his better than expected playoff performance provide evidence that he is a clutch player? Well, because this 13.9% contained more of this, like the whole season, let's assume that that is his ability. We'll use that. How likely is he to make exactly 12 shots? Well, again, exactly means we would use PDF. So we would have the binomial regular probability distribution frequency. And as far as the number of attempts, we're talking about the playoffs, and it says that he made 75 attempts. So that's what we're going to use as our N, our number of attempts, since we'd be like simulating the playoffs. So that's our N in this problem. Our probability is 13.9% or 0.139, and this wanted exactly 12. So we put that in the calculator. I think we've talked enough about that, and we end up getting 0.118 or about 11.8%. We won't do the calculator stuff for this. The setup's really what I'm freaking out about, okay? So this says, assuming his ability, again, is 13.9%, how likely is he to score less than 10 goals? Well, what numbers are less than 10? 9, 8, 7, etc., all the way down to 0. And remember, that is what the calculator tells us. And so less than 10 means that we would want to use the binomial cumulative distribution frequency with 79 attempts, a probability of 0.139. And this time, even though the number says 10 in the problem, we want to calculate what's less than 10. So we want to calculate up to 9. And then our calculator will give us 0.326. Or if you like percents, 32.6%. C is asking about making 15 or more shots. Well, 15 or more shots would mean that we would want 15 or 16 all the way up. However, that's not what our calculator can tell us. If we want 15 or more, that means we're going to have to take off 14 or less. So that means to get this, we would have to take 1 minus all of that, since those are complementary events. So we would take 1 minus the binomial cumulative distribution frequency. Again, we have 79 attempts, probability of 0.139, and then this time 14. Again, 15 or more, the complement is 14 or less. So we put that in the calculator, and we end up getting about 0.128 or 12.8%. Okay, so hopefully you're getting a little better with these setups. Now D is interesting. It says based on the probability you calculated in C, because this was how many shots that he made. And remember, we want to say that something is really good if he makes 15 or more. When we were talking about if something was, a performance was special, like when we were doing the hypothesis test. So is there convincing evidence that Crosby was a clutch player? Well, remember what we said is that things are unusual if they happen less than 5% of the time? Well, based on letter C, we get that there's about a 12.8% chance of that happening just by random chance if the ability is 0.139. So notice that that's more than 5%. So this doesn't say that Crosby was a clutch player. We would say no, because it's likely to happen by random chance. More than 5% of the time. If we had gotten a number like 3.2%, that would be less than 5%. And then we could say, yeah, that is pretty special because it's not likely to happen by random chance. But this just shows that his performance, that 15 of 79 or more, is not special because it happened by random chance more than 5% of the time. So again, E says, let's assume that same ability. How many shots would you expect him to make? Well, remember, expected value is N times P. So we would take 79 times 0.139. And if you take 79 times 0.139, we end up getting 10.981. So we would expect 10.981 made shots out of those 79. Okay. So again, the moral of the story, based on what we talked about, it's important to rethink each problem to think about what it means like for K or less, and then you can decide what number to use. So if this doesn't help, just kind of think about what we did here as far as those different values so that you could choose what you're going to put in the calculator. So for example, in letter A, when it says 15 or less, that means that we want 15 and everything to the left. So that means that we would use CDF with 15. However, less than 28 means that we would have 27, 26, 25, etc. So this time we would use CDF with 27. At most 12 means that we can have 12 at the most, but then also 11, 10, etc. So this is also a case where we'd use CDF 12. So you just, again, want to be careful because in some cases you use the same number that you see, and then in other cases you don't. So you've really got to rethink the problem. How about more than 22? Well, more than 22 means that we would want 23, 24, 25. But the calculator doesn't give us that. What we would have to do is we would have to subtract off 22. So we would use 1 minus CDF and use 22. 30 or more means that we would want 30, 31, 32. We would want 30 or more, which means that we would have to subtract off 29 or less. So we would want 1 minus the cumulative distribution using 29. At least 18 means that we would want 18, 19, etc., which means that we would have to subtract off 17 or less. So we would take 1 minus CDF using 17. So that's really the biggest thing, is what to use. Do you use PDF? Do you use CDF? Do you use 1 minus CDF? And then what number do you put in that spot? You can't just use the number that is given. You really have to think about the problem at hand, okay? So go ahead and get started on the assignment, and I'll see you guys soon. Thank you. Be good.